Welcome to this video. We're going to learn how to do some problems involving power production. First up is nuclear power. A nuclear power plant that uses plutonium-239 as fuel has a useful output of 14 megawatts and an efficiency of 45%. In the fission of one plutonium nucleus, this amount of energy is released. It's given. Determine the mass of fuel used per day. Assume the mass of plutonium-239 is 239U. So that's the mass of one nucleus. Let's go through the givens. They gave us the mass of one nucleus. They've given us the output power, which is the electricity you generate, and they gave us the efficiency. So you're putting in energy from the plutonium. The plutonium undergoes fission. That releases energy, but only 45% of your fission energy is actually going into electricity. The other 55% is lost as heat. Okay, what else do we have? This value is the energy released in each fission. That's the energy that every single fission or every single nucleus puts into the station. And again, out of this energy, just 45% of it makes its way to electricity. And we have to find the mass. Now, the first thing I want to point out is that they said assume the mass is 239U. In reality, the mass of one plutonium nucleus is a little bit bigger, but we're going to round it. So what's the total mass of plutonium that we put in? We are going to find this from the following equation. The total plutonium mass is equal to the number of nuclei we use times the mass per nucleus. So if the mass were 10 and we used 5, then 5 times 10 means we would have 50 as our total mass. But we see already that's not correct. We're going to have different values. To get this equation to work, to use this equation, we need to know what n is. We're going to find n from this equation. The total energy that is released is equal to the number of nuclei times the energy released per nucleus. Okay, so we have to get total energy before this equation can be used. How do we get the total energy? We're going to use the power equation. But before we can use the power equation, we have to use one other equation, the efficiency equation. Now, this is the power provided by the plutonium. The plutonium is the input power, and the electricity is the output. So we're looking here in this equation, we're looking to plug in or use the input power, not the output. All right, so once more, we're going to find the input power from this equation, and then we'll substitute it into the next one. From the next equation, we'll find the total energy released by all the nuclei together, and then we'll substitute that in right here. And then we'll find how many nuclei there are from this equation here, and we'll substitute that value in right here. And from that, we'll find the unknown, the total mass. So we start at the beginning. We know the output power is 14 megawatts of electricity. Mega is 10 to the 6. And the efficiency was given 0.45. So we calculate the power put in by the nuclei. Isolate P in, and it's this. On to the next equation. Now that we know the total input power from the plutonium, we plug that value in right here. And then we plug in the time interval. They wanted us to consider the mass used in 1 day, right? Per day, here it is. So the time we plug in is 1 day. But we can't plug in a day because a watt is a joule per second, not a joule per day. So we convert the days to seconds, and then we cross multiply, and E total comes to this value. Next, we use this equation. We now know this value, and we know the energy released in one reaction. So we plug in the total energy that we release over a full day, plug in the energy released by a single nucleus, and we divide to get the number of nuclei that fission per day. So that's how many nuclei we use in 1 day. Now all we have to do is convert that to a mass. So the number of nuclei times the mass of each nucleus gives us the total mass. We plug in the value from before, n that we just found. We plug in the mass of one nucleus. But we don't want the final answer to be in U, atomic mass units. We want it to be in kilograms. So you open your data booklet, you look up the conversion factor, and you use it to convert to kilograms. The U cancel out, leaving us kilograms, and the answer is this. Now we can actually convert this to a more appropriate unit. From kilograms, we can change it into grams by replacing the kilo with 10 to the 3. So this value times 10 to the 3 produces this many grams. That's a really small amount of mass to use in a single day. So you start to see the appeal of nuclear power. You get a lot of bang for your buck, so to speak. Every little kilogram has a ton of energy that it releases, and so you don't need that much mass on the whole. Here's another problem. The maximum power output of the Drax coal-fired power station in the UK is 4 gigawatts. Determine the minimum mass of pure uranium-235 that would be needed by a nuclear power station to provide the same maximum annual energy as the Drax power station. Okay, now here's what we're doing. We're saying there's this station which is coal-fired, but pretend for a second it used uranium. How much uranium would we need in 1 year, annual 1 year, to get the same amount of energy output? Okay, so we're sort of comparing the coal-fired power station with the nuclear, the fission, the uranium. The first thing we look is we see that there's this specific energy given. So let's write down the equation for specific energy. And again, we're looking for total mass. There's a specific energy equation. Or specific in physics means per unit mass. So specific heat has m in the denominator. Specific energy has m in the denominator. So, to use this equation, we'll need to know what the energy is. We have SE, but we need E. But are we looking for the energy of one fission? Are we looking for the energy of a day, the energy of a year? We want to find the mass for an entire year. So we need to plug in the energy for a full year. Now we're going to use the input energy for the full year because we're looking for the mass of uranium, and that mass of uranium is what puts in energy. The electricity is the output, and the input is the fuel. So how are we going to find En? Well, we're going to use the power equation. We know the power that's being put in. It's 4 times 10 to the 9, 4 gigawatts. And you're probably thinking, wait, isn't that the electricity? Isn't that the electrical output power? The answer is yes, that is the electrical output power. It says the maximum power output. But here's the reason we're using that as our input. They want us to find the minimum mass. So they want us to say, okay, pretend that every single kilogram of U-235, every single kilogram is used perfectly and there's none wasted. That lets us get the minimum mass. So if every single kilogram is used perfectly, none is wasted, and our input and output are exactly equal. Okay, so that's why the power input equals the power output. We're assuming perfect efficiency so we can get the minimum amount of mass. Now we plug in the amount of time. We're considering 1 year. We multiply both sides by this denominator value, and we solve for the energy put in over 1 year, assuming perfect efficiency. So we plug this in. We also know the specific energy from above. Tera is 10 to the 12. We isolate mass, and we solve.